So the question that comes up next is what happens when we move away from having prime moduli to composite moduli? So the first thing we want to look at is what happens when we simply replace that n by being a p into a p times q. So in this case, just a product of two little primes. What's going to happen in this case is that the procedure is going to be almost identical to what we did right here. The only thing that changes is we need to think a little bit about where that inverse should actually come from. And what ends up happening is that we need some other version of Fermat's little theorem that accounts for multiple primes. And that's where Euler's formula is going to come into play. And we're going to see various snippets of this thing as we go. So the first one that we're going to see is actually going to be Euler's formula for two little primes, in this case primes p and q. So let's go back and kind of show how this is all going to get unveiled. So the original starting point is going to be looking at Fermat's little theorem. So the idea is that if you take some number, raise it to the p minus first power, it's supposed to funnel me back into a 1. So what I want to do is I want to change that p into a p times q, so a product of two primes. Well, I'm going to have to add some extra stuff to my exponent probably. So what ends up happening is that it's really a pretty slick transition, is that if I want to move away from having a single prime to having two primes, so in this case two different primes, what ends up happening is that we get our first version of Euler's formula for a product of two primes, p and q. What this tells me is that if I raise some a to a p minus 1 multiplied by a q minus 1 power, that's again going to funnel me back into a 1 modulo p times q. So that tells me where I should begin to start looking for these inverses. So if you give me a nice congruence, if I know how that n actually factors, so if I know what p times q happen to be, the inverse d that I'm going to be looking for is going to be the inverse of e modulo p minus 1 times q minus 1. So let's go ahead and look at an example of this thing. So let's go look at the example. Okay, so I'm giving you this congruence. So it's of the form x to the 17th power is supposed to kick out a 1, 2, 3 modulo 12, 8, 3, 3. So right away from the get-go, I'm not actually telling you what those primes p and q happen to be, but because that n is so tiny, you can actually go ahead and factor that thing. So in this case, that n actually factors into a product of two primes, so in this case 41 times 313. And once I know how that thing factors, now I can actually go ahead and construct my inverse. So my inverse d is going to be the inverse of that exponent, so that's 17 modulo p minus 1 times q minus 1. So in this case, modulo 40 times 312. In this case, 17 is in fact coprime with that product. They don't share any factors. And if I run this extended Euclidean algorithm, you can actually see why that's going to be. Is that if I compute this thing, remember that this first cell is going to tell me what the GCD actually is. So I know that 17 is actually an invertible element, and I do in fact know what its inverse happens to be. So 17's inverse modulo 40 times 312 actually kicks out the answer of 5873. So now I know what my correct exponent is, so the overall solution to this thing is achieved the exact same way as it was when we had a mod a prime p. The only thing that changes in this world is how do I actually go and construct my inverse. So in this case, I had to know how n factored, so I needed to find these values p and q. Once I had that, I could compute this product p minus 1, q minus 1, and actually achieve the inverse of 17. In this case, it kicked out 5873. And if I compute this 1, 2, 3 raised to that massive exponent, do this power mod operation, it kicks out my answer of 11357. You can see that things become a little bit more complicated as my n becomes larger. So in this case, my n is quite a bit larger. I still have a composite n. And in this case, I actually know how it factors. And that's the huge if in this situation, is that if you don't know how that thing factors, things become very, very complicated. So the security of this thing is actually going to be connected to a factorization question, is that if I can easily factor that modulus, solving one of these things is really easy. You can see that it takes all of 1 or 2 lines in this case, is that you go ahead and factor that value n, which in this case factors as 8675309 multiplied by 8675311. So I have this nice twin prime in this case. So I have Jenny's phone number plus the next prime after it in this case. Those 2 numbers multiplied together give me my n. So that still assumed I knew how to factor that thing. If I couldn't factor that, I would be not nearly as set up as I am right now. So I'd be in a whole world of hurt in this case. I'd have to try a whole bunch of other things in this case. But for right now, I have this easy ability to factor that number n because it's not very big. As n becomes much larger, this game becomes way more challenging to play. So that's where we're going to be going in this case, is that as we begin to dive into this, we're going to need different types of factorization algorithms. Once we have a factorization algorithm, we can hopefully come back to actually attacking one of these things. But you can see that once we factor this value n, computing the inverse of that exponent is really easy. You have to take p minus 1 multiplied by q minus 1. So in this case, it's 8675308 multiplied by 8675310. So that's 1 less on each of those things. You're going to do this extended Euclidean algorithm operation on this thing. So this becomes that first cell. And then you're going to take it with 1, 2, 3. It's, in this case, going to return a fairly unpleasant value d, but it's still manageable in this case. What I do is I want to achieve this actual solution. All I got to do is I have to take that little base, this 5, 4, 3, 2, 1, raise it to this massive dth power, and then reduce that thing modulo that horrible new product n. In this case, it actually does fire off a somewhat unpleasant answer, but it does fire off something. I do, in fact, know how to solve this thing. It takes a couple lines of computation, but it is doable. And that's the huge if in this situation, is that if you give me some number n as my modulus, if you don't tell me how it's factored, I have to either A, try to factor this thing, or try to attack this congruence in some other fashion. If, and that's a huge if, I know how to factor this thing, everything is really easy. So the overall statement in this case is this following proposition, is that if you give me a couple primes p and q, the solutions to this congruence are achieved in the exact same way that it was last time. I have to make sure that my exponent e is in fact going to be invertible modulo p minus 1, q minus 1. So the GCD between p minus 1, q minus 1, and e has to be a 1. If that's the case, then this congruence is going to have a solution. The solution is going to be achieved by taking that c and raising it to the dth power. What's going to happen is that as you do the computation for this thing, you at some point in time are going to have to formally use this Euler's formula. That's the kicker in all of this, is that once you see this reduction, you're going to have this little bit that at some point in time is going to funnel into a 1. So it's nearly the exact same proof as the last one, except for what ends up happening is that when I have this expression and I'm going to do this inverse operation, what's going to happen is that I'm going to use a different fact to send it to a 1. So if you go back to this original argument, we had this c raised to this p minus first power. Well, in this case, if I was playing with just one single prime p, that goes to a 1 using Fermat's Little theorem. What's going to happen now is that when you replace this thing with the p times q, you at some point in time are going to have this exponent, which is going to be a p minus 1 multiplied by a q minus 1, and that's going to go to a 1 using Euler's formula. In this case, it's going to be using this little property right there. Later in the notes, I'll actually have a sketched out argument for why that thing ends up being true. What's nice is that not only is that going to be true, but we end up getting slight generalizations to this thing as well. One of the big kickers we're going to see is that if you replace that n with any general composite n, you can actually get a very nice statement that's going to say A raised to this Euler phi function. So this is this object that's going to count the number of things that are co-prime to that number n. We also last unit saw a connection to that thing and counting the number of generators. So this thing seems to reappear quite a bit. It's a pretty nice little object that we're going to be playing with quite a bit. If I take a number A and I raise it to that exponent, it again is going to send me to a 1 modulo n. So what ends up happening is that if I take a product of primes, so p times q, the Euler phi of that object is actually going to kick out p minus 1 times q minus 1. So it's pretty nice is that all of this stuff is built upon the same exact procedure. So I'm not going to go through the full argument of why proposition 3.1.11 is actually true. I'll actually pull it up real quick. Oh, maybe not. It's actually kind of dead on me right now. All right, so in this case, you can actually see that the overall argument for showing this overall construction of how to solve these congruences modulo a p times q is more or less the exact same step as before. The only thing that changes is that little bit right there. Everything I literally copy and pasted to show you that all of this is all interconnected is that there's one little change, and it's going to be what theorem do you actually apply. In this case, we are going to be applying Euler's theorem to actually clean up everything at the end.